Hello, my name is Yuchi Tian, PhD student in Columbia University. In this video, I will introduce my paper, Repairing Confusion and Bias Errors for DNN-Based Image Classifiers. Recent studies in DNN testing show that DNN-based classifiers are vulnerable to confusion and bias errors. Even robust trained model still has this kind of issues. Most of previous study in machine learning focus on general accuracy. In our studies, we focus on class-level errors, such as confusion and bias errors, which are very important for software engineering. Both confusion and bias errors are class-level errors. If a DNN model cannot distinguish between two classes, it is a confusion error. If a DNN model is biased toward one class than the other class, it's a bias error. For example, a DNN-based software used in a self-driving car may be confused between person and bus, because in training data, bus and person may always appear together. This is very dangerous. Another example, DNN-based software used in a zoo cannot distinguish between cat and tiger. It will also cause big problem. The confusion errors are important problem to software engineering because when we apply the DNN model in reality, those errors need to be repaired even though the overall accuracy is acceptable. In this example, because there is a baby in the image, a DNN model will be biased toward woman than man and predict this person holding the baby to be a woman. This may be because in training data, women and babies appear more in the same image than man and babies. Similarly, a DNN model will be biased toward man than woman in this outdoor sports image. This may be because in training data, man and sports appear more frequently together than women and sports. Gender bias is an important problem in software engineering. Our work focuses on repairing DNN models. First, to reduce confusion between a pair of classes. Second, reduce bias between two classes given a third class. Here is the formal definition of confusion and bias errors. Confusions are probability of misclassification between class X and class Y. There are two types of confusions. Type 1 confusion is for single label classification, where each image only has one label. So either X is misclassified as Y or Y is misclassified as X. We define type 1 confusion as the average value between the probability X is misclassified as Y and Y is misclassified as X. Type 2 confusion is for multi-label classification, where each image may have multiple objects and so multiple labels. Misclassification happens when class X in the image, class Y is not in the image. The model predicts both X and Y are in the images. We define type 2 confusion as the probability that one class is in the image, but the model predicts both classes. We define the bias errors as confusion discrepancy among a triple X, Y, and Z. Given class Z in the image, the difference between XZ confusion and YZ confusion is the bias between X and Y given Z. This indicates how biased between X and Y a model is given Z. In our previous paper published in ESEC 20, we proposed this neuron activation probability vector distance to identify confusion and bias errors. For each class C, we defined a vector PC. This vector consists of the average activation frequency of each neuron. ANI is the numbers of times neuron NI is activated, given the total N number of inputs with class C. We also use the altitude distance between Px and Py to indicate how confusing a model is confused between X and Y. The intuition is that if two classes always activate the same size of neurons, then the model cannot distinguish between them. If the distance is small, the model will be very confused between two classes. However, this distance metric is not differentiable, so we cannot use it in a loss function to repair. In this paper, we propose a feature space where each class will also be represented by a vector. The vector consists of the mean output of each neuron. This new space gives a more detailed granularity than activation frequency discussed in previous slides. We also propose a L2 distance between any two classes to indicate how confusing it is for a specific DNN model. And this distance is differentiable. We propose this loss function to repair the confusion errors. A new term is added to the regular loss function to increase the distance between class X and class Y during retraining. We propose another loss function to repair the Bayes errors. The new added term is try to make the distance between X and Z as close as the distance between Y and Z to reduce the Bayes between X and Y given Z. Both loss functions are easy to be applied into current DNN framework, and the overhead is small. We tested our approach on two models trained on two different datasets. The first model we try to repair is the state-of-the-art model trained with cut mix on CIFAR-10 dataset. The training process is exactly the same as the cut mix paper. The original model is trained for 300 epochs. We found out the model is most confused between dog and cat, so we use our new approach to retrain the model for another 60 epochs to reduce the confusion between dog and cat. The results show that our approach can reduce the dog and cat confusion by 14%, and the accuracy is very slightly reduced. We also test our approach on a multi-label classification model trained on Miss Coco dataset. This model is also trained in the same way as previous studies in Miss Coco dataset. We trained the original model by 30 epochs, and we found that bus is most confused with person. As you can see in the figure, we applied the new loss function after 30 epochs. The confusion starts to decrease to very low. The mean precision of the model, the green line, is even increased after we repair. The confusion reduction for CIFAR-10 models is not as significant as COCO model because CIFAR-10 is an easy task and its model and the test is already very accurate. Reduce the confusion further is harder than COCO model. Lambda is a trade-off between accuracy and the confusion bias reduction. Large lambda can even reduce confusion to 0, but with a large accuracy compromise. We didn't include the bias evaluation in this paper. It will be in future work, which we are currently working on. Thank you very much for watching. Please let me know your questions.